Find the coordinates of the stationary points on the curve y equals x, x minus 2 all cubed, and identify their nature. So we can see this is a product. So u is equal to x, and v is x minus 2 cubed. So du dx is equal to 1, and dv dx is going to be 3 x minus 2 squared, but the differential of the inside function here is just 1, so it just stays as 3x minus 2 squared. So we know we need to go that way first, so dy dx is going to be x minus 2 cubed, and then we're going to need to go the other way, and that is going to give me 3x, x minus 2 squared. Now, we've got a common x minus 2 squared here, and then from the first term we'd have x minus 2, and from the second term we'd have plus 3x. So that is x minus 2 squared, 4x minus 2, or taking a common factor of 2 out of there, we have 2 x minus 2 squared, 2x take away 1. For turning points, or stationary points, we want dy dx equals 0. Well, that means that x minus 2 squared, 2x minus 1 equals 0, giving me x is equal to 2, or x is equal to a half. Now, if x is equal to 2, looking at y would be equal to 0 because of the x minus 2 here. So we know that 2, 0 is one of our points. If x is a half, we'd have a half negative 3 over 2 cubed, which is a half times negative 27 over 8. So we've got a half and negative 27 over 16. So let's say we're going for the second derivative test and see what happens with that. So second derivative test. So we need to differentiate again, and it's probably best to go from that line there. And then we can just say, well, u is, I'm going to use the 4x minus 2 as the u, and the v is x minus 2 all squared. And then du dx is equal to 4, and dv dx would be equal to twice x minus 2 to the power 1. And again, the differential of the inside function there is 1. And so we can do that. Sorry, we'll go the other way first. So we can do that one first. And so d2y dx squared is going to be 4x minus 2 squared plus, going the other way, 2x minus 2, 4x minus 2, and I might say, well, that's 4x minus 2 squared plus 4x minus 2, 2x take 1. So if we think about that when x equals 2, the presence of those terms mean that that's just going to come to 0. So it's going to be 0, and therefore we get no further information from the second derivative test. We are going to have to use a sine test, either a first derivative sine test or a second derivative sine test. Now I'm going to do both. If we do d2y dx squared when x is a half, the presence of this term just here would make the second term 0. For the first term, we would get a half minus 2 squared in the bracket. Now that's going to be positive and times it by 4, so that is going to be positive overall. And when d2y dx squared is positive, that means that we have a minimum, and that would be at the half, negative 27 over 16. And we will look at this on the calculator as well. It's going to be quite a long example if you go through the whole thing. But for now, what we really need to do is investigate what happens with this one. Okay, so if we do the first derivative, sine test, we're looking at the one where x is 2. That was where our problem was. Now if we go to the left of that, say 1, well we know the gradient was 0 here. So if x is 1, then if we look at the terms over here, this one will end up being positive because it's squared. It doesn't matter what we put in there. And this one also will end up positive with x equals 1. And since we're multiplying those together, we know it's going to be positive. Let's look at 3. And once again, they're both positive. So positive. And therefore, the gradient goes positive, 0, positive. And that implies a horizontal point of inflection at 2, 0. Do we get the same thing with the second derivative sine test? So we go to 0. Sorry, 2. That's where our problem was. And we know the second derivative was 0 there, which is why we're doing the sine test to start with. Now, it's actually really difficult to go with 1 here. If I tried this earlier, this actually ends up being 0 at 1 as well. So we really need to go for something like 1.5, and then I'll go for 3.5. But I'm just going to do those on the calculator, and I'll pause while I'm doing that. Not quite sure why I went for 3.5. I could have gone for 2.5. But anyway, the values are on the calculator. And so we have that it's negative here and it's positive there. So what does that mean in terms of the curve? Negative means it's concave down. It then goes to 0 and then it goes concave up. And that once again indicates a horizontal point of inflection. And finally, I've got a picture of the curve here. And we can say analysis G solve. And our minimum here is at 0.5 or a half and negative 1.6875. which is our negative 27 over 16. And if we go for analysis G-solve and inflection, it's found the point of inflection that's in between the two stationary values. And there's our inflection at 2, 0, our horizontal one.